Okay, welcome to Mathematical Structure for Computer Science, CS 113, also known as Discrete Mathematics. In these lectures, we will go through what is a graph isomorphism. Again, this is Unit 10, lecture number 3-2, which cover chapter 10 of our course textbook. So our main objective is to go through isomorphism of graphs. So we start with the definition first. Here we say that if we have two simple graphs, G1 and G2, G1 have a vertex V1 and edges E1. G2 have vertex V2 and edges E2. And as we said earlier, graph consists of vertex and edges. Edges are the line that connects two or more vertices together. And we know that a simple graph is a graph that it doesn't have a loop. It doesn't have a loop. So here we are assuming we have two simple graphs, G1, G2. These two graphs are isomorphic if they have one-to-one and also onto function f from V1 to V2 with the property that A and B are adjacent in G1. And also if and only if f at A and f at B are adjacent in G2. So for all A and B in V1. So such a function f is called an isomorphism. So two simple graphs that are not isomorphic are called non-isomorphic. So the whole definition here is that if we have two graphs, let's say G1 and G2, first they have to have one-to-one relationship and also onto function f from V1 to V2 with the property that A and B are adjacent in G1 and also f at A and f at B will be adjacent in G2. Then we can say that these two graphs are called isomorphism, or they are again isomorphic. And again, we will go through an example soon and we'll get the point here. So here we have an example saying that we should show that the graphs G with vertex and edges, and the second graph is H with vertex W and edges F, are isomorphic. So we need to show that these two graphs are isomorphic. The main thing we need to show here is that if they have one-to-one relationship and also onto function. So first we look at the vertices. We remember one-to-one, we did that already, I think, in sets. The same concept here. If I have in functions, if I have one-to-one relationship in a function, it means one element in a function or set is connected to another element in another function or a set. So a one-to-one means we have to have exact number of elements in one function or a set with the second one. So we have two functions or two sets. If they are on one-to-one, it means if I have 10 elements in function 1, I also have 10 elements in function 2. The same concept here. Since we have two graphs, normally graph consists of vertices, so we need to check first. The number of vertices of these two graphs are the same. If they are not the same, then they cannot be isomorphism or isomorphic. So here we have 4. So this is a first prerequisite. Now let's say the edges also, we have 1, 2, 3, 4, 1, 2, 3. So we also have 4 edges. So there's a chance that these two graphs are isomorphic. So here the solution said the function f with f at u1 equal to v1, which is vertex u1, is the same as v1 here. It has 2 edges and also you have 2 edges. U1 have 2 edges in G, V1 also have 2 edges in H. Now, function or f at u2 is equal to v4. And we can look here, u2 have two edges, and it's in this one, v4, the same thing, two edges and the position. Then we have u3, f at u3 equal to v3, and f at u4 equal to v. So this is a one-to-one correspondence between v and also w. When we represent the v as the vertices in G, w is the vertices in graph H. So that's why we say one-to-one correspondence means the number of vertices in both graphs must be the same. Same thing, one-to-one in a function. The number of elements in the function, the two functions must be the same. Or if we are looking for one-to-one in a set, the number of elements in the two sets must be the same. So here they say we should know that the adjacent vertices in G are U1 and U2. You can see one adjacent U1, U2. Then we also have U1 to U3, and we also have U3 to U4 and U4 to U2. So that's what we. Then each of the pairs of F at U1 equal to V1 and F at U2 equal to V4, F at U1 equal to V1, and F at U3. So this tells us that they have the one-to-one correspondence. And also F at U2 is V4 and F at U4 is also V2. And F at U3 is V3 and F at U4 is also V2. So we can see how it goes. This consists of two adjacent vertices in H. You can see that each vertex also have two edges, adjacents. So this tells us that again, the two graph G and H, they are isomorphic. So isomorphism of graphs, here we say that it's difficult to determine whether two simple graphs are isomorphic using brute force. And brute force algorithm means we have to compare all the possible number of graphs and edges together. And the time complexity is very, very high. Brute force algorithm means if I'm doing something, I will do all the comparisons of everything or combination of everything to see if I get a solution. So that's why here it said the time complexity or the cost is n factorial. So we may have n factorial possible one-to-one correspondence between the vertex set of two simple graphs with n vertices. This is very costly, n factorial, which means if we have 20 vertices, then we have to do 20 times 19 times 18 times all the way to 1. The amount is too much, the possible combinations. So the best algorithm for determining whether two graphs are isomorphic have exponential worst case complexity in terms of the number of vertices of the graph. So we can see that as the number of vertices increase, the possible combinations also increases one-to-one. So that's why we say have a worst case exponential complexity. Also, sometimes it is hard to show that two graphs are not isomorphic. We can do so by finding a property preserved by isomorphism that only one of the two graphs has. Such property is called a graph invariant. So there are many different useful graph invariants that can be used to distinguish non-isomorphic graphs, such as the number of vertices, the number of edges, and the degree sequence. Degree sequence means the list of the degree of vertices in non-increasing order. And we will encounter others in later session of these lectures also. We have like 3 problems which we're going to address after the lectures. So this is another example. Determine whether these two graphs are isomorphic. So our theory said First, we should count the number of vertices and the edges. When we count, we say that both graphs have 8 vertices and 10 edges. So we can count 1, 2, 3, 4, 4. Also 4. Then we can see here we are missing 1 here and we are missing 1 here. So we are missing 2 here. So the number of edges and the vertices are the same. So we say they also both have 4 vertices of degree 2 and 4 vertices of degree 3. So we can also check the degrees. Degrees, how many edges are connected to the vertex. So this is 2 degree, this is 2 degree, this is 2, yeah, so that's correct. The rest is 3 degree here and 3 degree here also. But here we say, however, that's where we need to be careful. First of all, that's the condition. When I'm checking if 2 graphs are isomorphic, the first condition we check is the number of vertices we have and the edges we have for both graphs. But sometimes, in this case, the number of vertices, edges, and the degree of the vertices are the same. But still, however, G and H are not isomorphic. Why? We should know that since degree A is equal to 2, degree A is equal to 2 in G, a mass corresponding to T, because this is outsider. So the mass correspondence of outsider T, U, and S must be the same. So here we say, however, G and H are not isomorphic. The reason why, because the degree of A is 2 here in G, and mass corresponding to T, U, X, or Y in H. But because these are the vertices of degree 2, but each of these vertices is adjacent to another vertex of degree 2 in H, which is not true for A in G. So for example, let's see what they mean. We take the T here. We can see we have T, we have U, and we have S, the adjacents. And A, you can see here, we have D, then we have B. But A, when it connect to B, we have 3 edges. When A connect to D, we have 3 edges there. But when T connect to U, we have only 2 edges, and the other side 3. Now, when we take U also, U, we can see that we have 3 here, and also we have 2 here still. Remember A, we have 3 and 3 edges. Then when we take X, here is inner. We have 1 and we have 3 here. So here what we are trying to say is that the rules said in the isomorphic is that the degree of the edges in that very position must be the same connecting. So if I say A and T is the same, A have edge 2, goes to D with 3 degree, go to B with 3 degree, but T go to U with 2 degree and 3, so they are not. But each of these vertices is adjacent to another vertex of degree 2 in H, which is not true for A in G. So here you can see that in A, when I connect to a vertex is 3, the other one also is 3. But here, anyone we take, one of them will be 2. Even X is 3 here, but it's 2 here. And the rest, this is already 3, so we can't use it. A have only 2 edges, so we have to test with only 2 edges. But it goes here is 3, it goes here is 2, which is okay. When we take this also, this have 3 already, so we can't use it. This have 3 already, we can't use it. So we can only use X, Y, then T and U. And all of them, one of their adjacent vertex have 3 edges and one have 2. But in A, both have 3. So this is the main reason why it's not the two graphs are not isomorphic. So this actually will give us the conclusion of the whole concept of isomorphic graphs. Two graphs are isomorphic when they have the same number of vertices and edges, but also the degree of their adjacent vertices must be the same also. So here they are not the same. Here we also say that alternatively, note that the subgraph of G and H made up of vertex, degree, tray, and the edges connecting to them must be isomorphic, but the subgraphs as shown on the right are not. We can see these two, they are not also. Also the main reason, the degree of the adjacent vertices. So three things we need to consider. The previous example, as we can see, let's go first example here. First of all, look at both. This is very straightforward. You can see that every vertex have only two adjacent vertices. Everyone is connected to two, everyone. So this easily make it. We count the number of vertices 4, 4, the number of edges 4, 4, and also the number of degree of the vertex is 2, 2 throughout. So this is tell us that G and H is again isomorphic graphs. By here we can see that A, we have 3, connect to B is 3, the degree is 3 at B, connect to D, the degree also is 3. But if I take, first of all, A have 2 edges, so I'll look at all the vertices that have 2 edges, which is X, Y, T, and U. But it seems like U is good, but when I look at the U adjacent vertex of S, it have 3 connections. That's good, we have 3. But here, the U have only 2. Instead of 3, also 3 edges, so the degree should be 3. So that alone makes these two graphs not isomorphic graphs. So another example here again, we have determined whether the two graphs here are isomorphic. So the first thing we need to do again, the same thing, we count the number of vertices 1, 2, 3, 4, 5, 6. The second one, 1, 2, 3, 4, 5, 6. The number of edges, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I see 1, 2, 3. 1, 2, 3, 4, 5, 6. So, okay. So first thing we check is everything look good here. The number of edges and vertices for both graph G and H is the same. Now we can start to. This is where we don't want to use the brute force. Brute force means we're going to compare all the edges with each other to see the degrees will match. And that's not the best thing to do. So that's the solution here. Both graphs, as we said, have 6 vertices and 7 edges, which is good. So they also both have 4 vertices of degree 2 and 2 of degree 3. And the subgraph of G and H consists of all the vertices of degree 2 and the edges of connecting them are isomorphic. So it is reasonable to try to find an isomorphic. So as we said earlier, we can check and see. I can stand at this U1 and V1. I compare the two. V1, yeah, it gave me 2, and this also gave me 2. And I come here, I have 1, 2, 3. This is 1, 2, 3. I have here 1, 2. This is 1, 2. I have here, I'll say the V6 and U6 should go 1, 2, 1, 2. So we can see that again, the degrees are the same in their positions. Some of them have 3, some of them have 2. And the inner one here, V is 2. V2 and V6 are 2 degrees. Here also the same thing, U5 and U6 is 2 degrees. Outsiders, and this is 2, this is 3, this is 3. So they are the same. So here we can define an injection function from the vertex of G to the vertex of H that preserve the degree of vertices. And also we'll determine whether it is an isomorphic. So this is how we check and everything look good, but again, this is how it goes. So a function f with u1 to v6. So we are connecting u1 with v6. We have 2, 2, 2. It's a 1-to-1 correspondence between G and H. Now, showing that this correspondence preserve edges is straightforward. So we will omit the details here. Again, because F is an isomorphism, it follows the whole concept here. So again, the whole thing, 3 things that we consider again: the number of degrees of each vertices, of course, the number of vertices, and also the number of edges. Since here they are all the same, we say the two graphs are isomorphic graphs. So the algorithm for graph isomorphism, here we say the best algorithm node to determine whether 2 graphs are isomorphic have exponential worst case time, because of as exponential function means the function increasing slowly, but as the input is increasing, it will increase exponentially because the input value is an exponent. So 2 to the power 1 is only, let's start from 2 to the power 0 is only 1. 2 to the power 1 is only 2. 2 to the power 2 is only 4. We can see the difference is not too much yet. But 2 to the power 3 goes to 8. Now we move from 4 to 8. Not only that, 2 to the power 4 is moving to, I think 32 or 16, 8 to 16. So we can see that it's increasing exponentially. So that's what we are explaining here. It's still the best algorithm, but it has a exponential worst case time complexity. However, these are algorithm with linear average case time complexity. So we can use the public domain program called NUTI to determine in less than a second whether 2 graphs with as many as 100 vertices are isomorphic. So this is an application online. I think it's also free access. Also, graph isomorphism is a problem of a special interest because it is one of the few NP problems not known to be either tractable or NP complete. NP problems are normally problems that is difficult for us to solve using computer algorithms. So there are so many applications for graph isomorphism. This textbook gave us, our course textbook gave us 2 examples. Chemists use molecular graphs to model chemical compounds. This is again isomorphism graphs. So vertices represent the atoms and edges represent the chemical bonds. Also, electronic circuits can be modeled as graphs in which the vertices represent the components and the edges represent the connections. So I may have a resistance or electric light. The electric bulb will be a vertex, and the line connecting the 2 bulbs or connecting to the switches will be the edge. So now let's go through some questions here. Here they say we should determine whether the given pair of graph is isomorphic. First, we check how many edges and vertices we have. 1, 2, 3, 4, 5. And here we have 1, 2, 3, 4, 5. Okay, so they are all, and also edges 1, 2, 3, 4. The edges here 1, 2, 3. So it's also 4. Now we need to check with the degrees now. We can see that here our U1 have only 1 degree. Only 1 degree. So we can still represent it with V1. V1 also have only 1 degree. The 1 degree connect to U2, and U2 have 2 degree because to U2 go to U1 and U3. Same thing here, V2 connect to V4 and V1, so you have 2 degree. So this is how we check it. We go to U3, we have 2, and then we can take E3 with V2, we have 3, or I'm sorry, 2. Okay, good. So we said these graphs are isomorphic since each path with 5 vertices. First, each path 5. Then one isomorphism is f at u1 is v1 as we said earlier because they have 1. And also f at u2 should be v2, yeah, because it goes here 1 and 1, so 1 and 1. Then f at u4 we go with v5. So we have u4. F at u4 go with v5. v5 have 2. You also have 2. Then you can see that the u5 will go with v3 because it's only one connection. So f at u5 is v3. So this is so as we said, to check if a graph is isomorphic or not, two graphs, and that's a simple graphs. First, again, check the number of vertices. Second, check the number of edges. They have to be the same. Then third, we look at the degree of each vertex to compare. So the degree of the vertex now will give us the 1-to-1 correspondence. Of course, the number of edges, vertices also give us 1-to-1 correspondence. So let's see the second question. Determine whether the given pair of graph is isomorphic. First thing we check again is the number of vertices. We have 1, 2, 3, 4, 5. Here we have 1, 2, 3, 4, 5. The number of edges we have 1, 2, 3, 4, 5, 6, 7. Here we have 1, 2, 3, 4, 5, 6, 7. Okay. So now we need to do our comparisons now. Here they say these graphs are not isomorphic. Now this is why we said the algorithm to check whether two graphs are isomorphic. Don't use the brute force. Brute force means I will take U1, compare all the elements in the second one until I get 1-to-1. Then I take U2, compare all of them. Right now, compare one already, so the rest I will compare to. So you are doing combine, it's a lot. The time complexity is very high. So you can see that even with only these few vertices, which is somewhere around 5, we still have to be careful comparing. So for example, I'll look at V5. V5 have 3 degrees. And I'll come here. Okay, we have 3 degrees with this. So I'll take V2. Yeah, we have 3 degrees here also. So V2 have 1, 2, 3, 4. So V2 have 4. In this graph, we don't have any vectors with degree of 4. 1, 2, 3, 1, 2, 3, 1, 2. So this is where I'm going to stop. Because the second graph here, the V2 have a degree of 4. But the first graph, we don't have any vectors with a degree of 4. So I'll stop right there. So that's the answer. These graphs are not isomorphic. The second has a vertex of degree 4, whereas the first does not. So again, to repeat, this is a very straight algorithm. The only problem is the time complexity. The more vertices we have and edges, the more time we are going to compare, waste time, more time we are going to spend to compare. But it's very straightforward. We want to make sure the number of vertices are the same, the number of edges are the same, and we check the degree of each vertex must match 1-to-1 to the second graph. So let's look the last question here. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The same question, we are checking if the two graphs are isomorphic. So we can see the number of vertices. If the number of vertices are not the same, we stop. Quick way to say they are not. The edges, we have 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 2, 3, 4, 5, 6, 7. It seems like 8, 8. Now we have to look at since the number of vertices and the number of edges are the same for both graphs. Now we look at the degree. Normally what I do is I will look at the vertex with the highest degree in one of them, then I'll look at the left if I can get the same. So for example, I look at V5, I have 1, 2, 3, 4. Yes, I have 1, 2, 3, 1, 2, 3, 4 for U2 also. Then I have another 1, 2, 3, 4. So let's see if we can get another 4. This is 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so this is, we're going to stop because here we have 1, 2, 3, 4. And for V3, we have 1, 2, 3, 4. Here we have only 1, 2, 3, 4. And we don't have another 4 again, unless I'm missing now. So we said this, but the answer said that these two graphs are isomorphic. Each consists of K4 with fifth vertex adjacent to two of the vertices. In K4, many isomorphisms are possible. So let's say U1 and V1 is the same. U1, we have 1, 2, 3, V1, 1, 2, 3, okay. Then U2 and V3, U2, 1, 2, 3, 4, V3, 1, 2, 3, 4. And then V2, U3 and V2, U3, 1, 2, V2, 1, 2, okay. Then U4 and V5, okay, I missed this. So U4 is 1, 2, 3, 4. I was counting it as 3. So 1, 2, 3, 4. So that means they are the same because all I'm looking for the highest 1, 2, 3, 4, 1, 2, 3, 4. So I have also 1, 2, 3, 4. Then down here 1, 2, 3, 4. Then this is 1, 2 with the V2. So they are isomorphic. Again, very straightforward. The number of vertices here for both graphs are the same. The number of edges are the same. My last check now, I want to have the same one-to-one correspondence about the number of degrees. So what we mean here is that if I have two vertices in my first graph, which I have a degree 4, I have to have the same second graph. I have to have the same amount of two vertices with the same degree 4. Otherwise, they are not. So the number of degrees you have for the first graph should be the same as the number of degrees you have for the second graph. So hopefully this will help us understand the concept of isomorphism in graphs. Again, here we are dealing with simple graphs. Two simple graphs are isomorphic if the number of edges and the number of vertices are the same, and the degree of the vertices of the first graph is the same as the second graph, the numbers are the same. So this will be the conclusion of our lectures. And again, if you have any question, you can send an email. So wish everybody the best and thank you.